Somewhere past Neptune, in the coldest, quietest region of the solar system, a world spins so fast that its entire day is over before you'd finish a shower. Its name is Haumea, and its shape is wrong, not damaged, not eroded, wrong from the moment it finished forming. Astronomers confirmed that shape in 2008, and most people who've heard the phrase dwarf planet have still never heard of it. Its longest side stretches 736 miles farther than its shortest. It completes one full rotation in 3 hours and 55 minutes, faster than almost anything else its size anywhere in the solar system, and it finishes one full orbit of the Sun only once every 284 years. Tonight, we'll uncover 4 things about Haumea that don't add up. The collision that may have built it, the trail of debris it left scattered across the dark, the 2 moons still bound to its wreckage, and the dark red scar on its surface that scientists still can't explain. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Stand at the equator of Haumea. If anything could survive the cold long enough to stand anywhere on it. And let a stone fall from your open hand. Before it lands, the ground beneath your boots has already carried you sideways faster than a point on Earth's equator moves in that same stretch of time. Because the world underneath you never stops. That single fact breaks an assumption almost nobody thinks to question. That big planets move fast and small worlds sit still. Haumea is barely a third the width of Earth, a frozen scrap of rock and ice drifting far past Neptune. And yet a spot on its surface crosses more ground every hour than a spot on ours does. The difference isn't size. It's how fast the whole body is turning underneath whoever, or whatever, is standing on it. A full day on Haumea, sunrise to sunrise, if there were a sun close enough to notice one, lasts 3 hours and 55 minutes. Long enough to watch a movie, not long enough to finish a full night's sleep. Spin something that fast, and the ground itself stops behaving like solid rock. It starts behaving like water flicked off a wet hand. It wants to leave. Here's what almost nobody considers about spin at that speed. It doesn't just move the ground faster. It changes how hard the ground is willing to hold you down. Stand near Haumea's stretched equator, and you weigh measurably less than you would standing at one of its blunter, compressed poles. Same body, same you, 2 different pulls. Depending only on where your feet happen to be. Drop the stone at the equator, and for a fraction of a second before gravity wins, that stone is already being flung sideways by the same spin trying to fling you. It still falls. Gravity still wins in the end, but it falls along a curve, not a straight line, and the curve is dictated by a rotation so fast it has physically reshaped the world producing it. Astronomers never watched that rotation happen directly. From 4 billion miles away, a body barely wider than the length of the United States is far too small and dim to show a turning face to any telescope, even Hubble. They found the spin a stranger way, by watching Haumea's light. Every 3 hours and 55 minutes, it brightens, then dims, then brightens again, in a rhythm steady enough to set a stopwatch by. That rhythm is the signature of a body that isn't round. A sphere shines the same no matter which way it turns. There's nothing to blink. Haumea's light rises and falls twice in every single rotation, because as it spins, it shows first a wide face to the distant sunlight, then a narrow one, then a wide face again. The brightness was drawing the shape long before anyone had a picture of it. But a light curve only proves a shape is stretched. It doesn't say how far. And the true numbers, when astronomers finally pinned them down, were more extreme than anyone had guessed going in. 1,440 miles across its longest axis. Roughly 1,060 across its middle. Only about 700 across its shortest. 3 different widths for the same object, depending entirely on which direction you happen to be measuring. No planet does this. No ordinary moon does this. Round worlds have a single number that answers the question, how big is it? Because gravity, given enough time and enough mass, pulls everything toward the same distance from the center. A sphere is simply what a large enough object looks like once gravity has finished arguing with itself. Haumea looks like the argument never finished, or like something forced a new argument onto a body that had already settled the first one. Picture a ball of dough spun hard on a fingertip. It doesn't stay round. It flattens, stretches, reaches outward, along the direction it's spinning while pulling in along the other two, not randomly, but along three distinct, almost architectural axes. Haumea's shape follows that same logic, except nothing is holding it up, nothing is reforming it by hand, and it has apparently held that stretched form for longer than anyone can currently prove. The first serious attempt to measure those three axes came in 2006, when astronomer David Rabinowitz and colleagues used Haumea's brightness variations to estimate a shape roughly similar to what's accepted today, though considerably less precise. Early figures put the longest axis anywhere from about 1,300 to 1,500 miles, a range wide enough to leave genuine doubt about exactly how extreme the distortion actually was. It took another 11 years, and a far more direct method, to narrow that range down to something astronomers could finally treat as settled. Walk in a straight line from Haumea's widest point to its narrowest, and you'd cover a distance longer than a walk from New York City to Pittsburgh, on a surface that, by every rule geology usually follows, should have relaxed back into a sphere a long time ago. It hasn't. Something is keeping it stretched, and it isn't scaffolding, and it isn't rock strong enough to resist its own gravity. Ice and rock at Haumea's temperatures behave more like a slow, cold fluid than like stone. Given enough time, that kind of material flows. That kind of asymmetry carries consequences beyond geometry alone. Surface gravity, the pull under your feet, even the direction down would mean something different depending on exactly where you stood. A detail this episode returns to later, once Haumea's mass has been pinned down precisely enough to work the numbers out in full. The most precise outline of the shape came from a strange event in 2017. Haumea passed directly in front of a distant star, and astronomers on 10 different telescopes scattered across Europe watched the star's light blink out, then reappear, timing the shadow to the second to trace the object's true silhouette against the dark. That occultation was only supposed to measure a shape. It also caught something none of the 10 telescopes involved were specifically looking for. Something we'll come back to. What none of this explains, not the light curve, not the 10 telescopes, not the precise mileage of each axis, is why the shape holds instead of relaxing. A ball of dough spun that hard on a fingertip collapses, or tears, or slides off entirely within seconds. Haumea has done neither, not for as long as anyone has been able to measure it. In 1834, a German mathematician named Carl Gustav Jacobi worked out something that had nothing to do with astronomy and everything to do with fluids. He wanted to know what shape a spinning body of liquid, held together only by its own gravity, with no solid crust, no scaffolding, nothing but self-attraction fighting against rotation, would settle into once it stopped changing. Spin it slowly, he found, and it flattens into a smooth, symmetrical disk, wider at the equator than at the poles, the same shape a soft ball of clay takes when you press it between two palms. Spin it fast enough, past a specific threshold, and the answer changes completely. The body stops being symmetrical at all. It stretches into a shape with three distinct, unequal axes, long, medium, short, locked at specific proportions to each other, dictated entirely by how fast the whole thing is turning. Jacobi wasn't working in isolation. A few decades earlier, the Scottish mathematician Colin Maclaurin had already worked out the slow spin half of the same problem. The smooth, symmetrical flattening every schoolbook illustration of a spinning planet still assumes. Jacobi's contribution was proving that Maclaurin's tidy, symmetrical answer wasn't the only stable option available. Past a specific spin threshold, an entirely different, less symmetrical family of solutions took over, and a body crossing that threshold wouldn't ease gradually from one shape to the other. It would jump. Jacobi never saw a body do this. There was no way to see one in 1834. He solved it on paper, with no object in mind, decades before anyone in his field seriously entertained the idea that any real astronomical body might ever spin fast enough to need the answer. Here's the part that took over a century and a half to land. When astronomers finally measured Haumea's 3 axes precisely enough to compare them, the proportions matched Jacobi's abstract solution almost exactly. For a body of Haumea's estimated mass and density spinning at its measured rate, Haumea's own axis ratios come out close to 2 to 1 to 1. The long axis roughly double the short one, the middle axis sitting nearer the short end than the long, proportions that fall squarely inside the narrow band. Jacobi's mathematics allows for a stable ellipsoid, rather than the much broader range of shapes a body could take if the physics allowed anything at all. Not roughly. Not in the same ballpark. Close enough that Haumea is now used, in its own right, as one of the clearest known real-world examples of a Jacobi ellipsoid anywhere in the solar system. That match means something specific and stranger than it first sounds. Haumea's shape isn't a scar. It isn't leftover damage healing slowly back toward round, the way a dented planet might. It's an equilibrium. The exact shape a body made of ice and rock at Haumea's density is supposed to hold, given how fast it spins, for as long as the spin stays roughly constant. The math didn't just describe Haumea after the fact. It had already specified, on paper, in a study of idealized fluids with no astronomical body attached, precisely what shape a real world would be forced into if one ever spun this fast. You could know nothing about Haumea, sit down with Jacobi's 19th-century mathematics and nothing else, and derive the outline of a world 4 billion miles away that nobody would photograph clearly for another 170 years. That still leaves the harder question sitting untouched. An equilibrium shape only holds if the spin itself holds. And spin, this extreme, doesn't have unlimited room to exist in. Jacobi's equation has a ceiling. Push the rotation rate high enough, and the elegant 3-axis ellipsoid stops being the answer entirely. The body's long axis keeps stretching. The waist keeps narrowing, until the shape stops looking like a stretched ball and starts looking like a peanut. A single body pinching itself toward becoming 2. Physicists have a name for the point just past where Jacobi's solution runs out. The sequence doesn't fail gently. It runs directly into instability, the mathematical last stop before an object either flies apart or splits into a pair of smaller bodies orbiting each other. The full sequence of possible shapes, worked out in more detail by the French mathematician Henri Poincaré later in the 19th century, doesn't stop at ellipsoids either. Push rotation higher still, and the mathematics predicts a further transition. The ellipsoid's narrow waist keeps pinching until the body develops a distinct bulge at one end, a shape closer to a pear than to anything symmetrical. Right before the sequence runs out completely and the body is expected to split in 2, Haumea shows no sign of reaching that pear-shaped stage. Its measured proportions sit cleanly inside the ellipsoid range, which is part of why the Jacobi match is treated as meaningful rather than approximate. Haumea sits close to that ceiling, not past it, close to it near enough that its measured spin puts it right at the upper edge of where a Jacobi ellipsoid is still the stable answer, rather than the beginning of something worse. Researchers who've modelled the margin put it at somewhere around 10 to 20% above Haumea's current rotation rate before the body would be expected to cross into that unstable pear-shaped regime, close enough that Haumea sits nearer the edge of the range than the comfortable middle of it. Think about what that means in practice, not in equations. A body drifting alone in the dark, 4 billion miles from anything, has been holding a shape that sits one adjustment away from a completely different outcome. Speed the rotation up by a modest fraction, not dramatically, not by half, just enough. And the same physics that currently holds Haumea together as a single stretched world would start pulling it toward pinching in half. It hasn't pinched. As far as anyone can measure, it hasn't sped up or slowed down enough to threaten the balance in a very long time. But sitting that close to a threshold for any length of time raises an uncomfortable question underneath all the others. What kind of event spins a body up that close to its own breaking point in the first place? Slow, gradual processes don't usually produce numbers this extreme. Something abrupt usually does. Nothing about a body forming calmly, out of the same slow accumulation of ice and dust that built every other object nearby, gets you to 3 hours and 55 minutes. Objects that form gently spin gently. Whatever gave Haumea its spin did not arrive gently, and it did not arrive slowly, and it left more evidence behind than just the shape. Somewhere in the first few 100 million years after the solar system finished its rough draft, while the ice giants were still migrating outward, while the belt of debris that would become the Kuiper Belt was still a churning, crowded field instead of the quiet scatter it is now. Something struck Haumea, not scraped it. Struck it, hard enough and at the right angle to leave marks that have lasted for billions of years afterward. A rotation faster than a planet's, a shape stretched past anything gentle formation could ever produce. And, as it turns out, a great deal more than that. A single well-placed impact, early enough and violent enough, does something a slow, calm formation never could. It doesn't just dent a surface. It can transfer an enormous amount of spin directly into the body it strikes. The same way a glancing hit on a spinning top changes not just its position, but the rate at which it keeps turning afterward. The physics is a matter of leverage as much as force. Strike an object off-center, near its outer edge rather than its middle, and a comparatively modest impact can impart a wildly disproportionate amount of rotation, precisely because the force is being applied as far as possible from the object's center of mass. Strike a young, half-formed world at the right angle, hard enough, and you don't just leave a crater behind. You leave a different rotation rate behind, one that has nothing to do with how the object originally came together. Reconstructing exactly how much spin a single strike could plausibly deliver requires modeling the impactor's size, speed, and angle together, not just gesturing at something big hit something. Researchers running those numbers for Haumea have found that an impactor several hundred miles across, striking at speeds typical for the crowded early Kuiper Belt, hitting off-center rather than head-on, comfortably supplies enough angular momentum to explain the measured spin, without requiring an object so large, or a collision so improbable, that the scenario starts to strain credibility on its own terms. That detail matters for how seriously the hypothesis gets taken. An explanation that only works by invoking a wildly improbable, 1 in a billion years event is a weak explanation, however neatly it fits the data. An explanation that works with an ordinary-sized impactor, moving at ordinary speeds for its era, striking at a geometrically reasonable angle, is a different kind of claim entirely, the kind that doesn't need special pleading to be taken seriously. That single explanation, on its own, does a remarkable amount of work. It accounts for the extreme spin. It accounts for a shape sitting almost exactly where Jacobi's mathematics says a body turning that fast should sit. It even offers a reason why a small, distant, otherwise unremarkable world would have anything left over nearby at all. Companions, debris, scattered pieces still drifting close, still carrying the fingerprints of wherever they came from. But here's what turns a tidy hypothesis into an actual investigation. A single collision that violent shouldn't just leave the body that got hit spinning strangely, it should leave wreckage. Somewhere in the region around Haumea, if this idea holds up, there ought to be pieces. Fragments knocked loose, flung outward, still orbiting nearby with the same chemical signature stamped into them. Astronomers went looking for exactly that. What they found didn't just support the idea, it turned Haumea from an oddity into the center of the only confirmed case of its kind anywhere in the outer solar system. Before any of that evidence gets its own turn, though, there's an earlier, stranger story attached to Haumea, one that has nothing to do with physics and everything to do with two teams of astronomers several thousand miles apart, both convinced they'd found it first. In late December of 2004, a team led by astronomer Mike Brown at Caltech spotted a faint, slow-moving point of light in images taken at Palomar Observatory in California. They gave it an internal nickname before they gave it a real one. Santa, for when it turned up, and kept observing it quietly through the first half of 2005, gathering enough data to be certain of what they had before announcing anything to the world. That's the normal pace of the work. Confirm the orbit. Confirm the size. Confirm you're not about to embarrass yourself in front of every other astronomer on the planet. They never got the chance to announce it on their own timeline. On July 27th, 2005, a team led by astronomer José Luis Ortiz, working from the Sierra Nevada Observatory in Spain, submitted a discovery notice for the same object days before Brown's group had planned to go public. Ortiz's team said they'd found it independently, in older archived images from March of that year. Brown's team noticed something else almost immediately afterward. Server logs from the telescope data his group had been using showed that someone from an IP address in Spain had accessed their observation records that had briefly, and by mistake, been left viewable online. In the days just before Ortiz's announcement went out, Brown has said, in his own public account of the episode, that he chose not to formally contest the discovery credit, despite what those access logs suggested to him. He has also said it's one of the only professional decisions from that period he still second-guesses. Ortiz, for his part, has consistently maintained that his team located the object independently while reprocessing older survey images for an unrelated project, and that the timing was coincidence rather than anything else. The International Astronomical Union ultimately recognized Ortiz's team's submission, and with it, naming rights for the object, rights that would eventually give the world the name Haumea, chosen specifically because of what astronomers already suspected might be orbiting alongside it. The rivalry wasn't unique to this one object. The same several years produced Eris, another icy world whose discovery, also credited largely to Brown's team, helped trigger the 2006 vote that stripped Pluto of full planet status. It was a short, unusually competitive window in astronomy. Several genuinely new worlds turning up within months of each other. More than one team racing to be first across the finish line with an announcement. Nobody has ever definitively proven the timeline Brown suspects. Ortiz has maintained his team's claim was independent and legitimate. No formal misconduct finding was ever issued against anyone involved. What's left, 2 decades later, isn't a verdict. It's an asterisk, a quiet, permanently unresolved question mark sitting underneath the official record of who found one of the strangest objects in the solar system first. Discovery disputes like this one aren't unique to Haumea, even if the specific details of this one are unusually pointed. The history of astronomy carries more than one contested who found it first story. From arguments over the discovery of Neptune in the 1840s to quieter, less publicized disagreements buried in survey logs across the 20th century. What sets Haumea's case apart is simply how well documented the modern version is. Digital server logs, time-stamped announcements, public statements from both sides. Leaving a paper trail earlier disputes never had the chance to generate. The name that eventually stuck came from somewhere far older than either team's dispute. It turned out to fit better than any naming committee could have planned for. Haumea is the Hawaiian goddess of fertility and childbirth, closely tied in tradition to the island of Hawaii itself. In some accounts, she isn't just associated with the island. She is the island, its rock and soil treated as an extension of her body. Across different versions of her story, she gives birth again and again, to daughter after daughter, and not gently. Several accounts describe her children emerging from different parts of her own body, through processes closer to violent transformation than ordinary birth. She loses pieces of herself in the act of creating something new, over and over, and keeps going anyway. Different tellings place her origin differently, sometimes as a figure who arrives in Hawaii from a more distant, more mysterious homeland. Other times as a being who simply always was, present at the start of the islands themselves. What stays consistent across the versions is the pattern: creation through repeated, costly acts, rather than a single tidy origin story. She isn't a goddess who makes things once and rests. She keeps making things, and each act appears to take something out of her in the process. The specific naming decision fell to a working group within the International Astronomical Union, responsible for approving names for trans-Neptunian objects, a small committee that reviews proposals against the region's established naming conventions before anything becomes official. Discovery teams typically suggest a name, but the committee can push back, request alternatives, or spend months deliberating before signing off. A bureaucratic process that sits at odds with how immediate and inevitable the final choice can feel in hindsight. In Haumea's case, the process took roughly 3 years from initial detection to formal naming. Time spent partly on the ordinary business of confirming the object's orbit, and partly, by several accounts from those involved, on making sure a name this loaded with meaning was the right one to attach permanently to an object this strange. When astronomers assigned this dwarf planet its permanent name in September of 2008, that mythology wasn't background trivia. It was the entire point. By then, they already knew Haumea had 2 moons. They already suspected correctly, as it turned out that a scattered family of icy fragments shared its orbit and its chemistry. Fragments that looked exactly like pieces knocked loose from the same body. A world that appears to have been struck hard enough to fling parts of its own icy shell outward, hard enough to leave 2 smaller bodies still bound to it afterward, isn't just named after a goddess of childbirth by coincidence. It's named after her because the resemblance was, by the time anyone chose the name, already impossible to ignore. The 2 moons received names to match. The larger one became Hi'iaka, after one of Haumea's most celebrated daughters, patron of the big island itself, born. In the version of the story astronomers leaned on for the name, from an unusual and painful delivery, the smaller, more distant moon became Namaka, a daughter associated with the sea, tied in different tellings to water, distance, and a more turbulent relationship with her siblings. You don't need to believe in any of it to notice the fit. A body that seems to have been struck hard enough to lose part of itself, that carries 2 smaller companions born out of that same violence, sitting under a name that has meant exactly that story for longer than telescopes have existed. Sometimes the oldest language available turns out to describe the newest discovery more precisely than anything invented afterward. Hi'iaka, the larger of Haumea's 2 moons, measures roughly 190 miles across, barely bigger than a mid-sized American county, stretched out and set drifting through the dark. It orbits Haumea once every 49 days, in a path close enough to circular and close enough to Haumea's equator that its motion looks almost deliberate, almost engineered, for something built entirely out of leftover collision debris. Astronomers first spotted it in January of 2005, only weeks after Brown's team had begun tracking Haumea itself under its Santa nickname, using the same instrument at Palomar that had already flagged the parent body as strange. Namaka is smaller, fainter, and stranger. At roughly 70 miles across, it's little more than a large asteroid by width, discovered a few months after its sibling, in June of 2005. Its orbit doesn't behave the way Hi'iaka's does. It's more elliptical, more tilted relative to Haumea's equator, less settled. A moon that looks, even at a glance, like it hasn't finished working out where it belongs yet. At the time of discovery, its faintness pushed the limits of what ground-based telescopes could reliably confirm at all, and its orbit wasn't pinned down with real confidence until several additional years of follow-up observation had accumulated. Neither moon looks like an object that formed the ordinary way, gathering slowly out of its own patch of space over millions of years. Both share Haumea's unusual surface signature: water ice, and lots of it, layered over surfaces far brighter than anything else typically found this far from the Sunday. That shared chemistry is the detail that matters most. It's not the kind of thing two unrelated objects develop by coincidence. It's the kind of signature you'd expect if both moons were once part of the same icy shell Haumea appears to have lost. Their combined mass is a small fraction of Haumea's own. Together, the two moons amount to only a few thousandths of the parent body's total mass. A detail that matters for the physics of the collision itself. Whatever event separated them didn't need to remove a large share of Haumea's total material. It only needed to remove the right material, from the right layer, at the right velocity, to end up orbiting rather than escaping outright. Follow-up observations over the years since discovery have refined both moons' sizes considerably from the first rough estimates. Early size calculations, based only on brightness and an assumed reflectivity, carried enough uncertainty that Haumeia's diameter was quoted anywhere from roughly 150 to 220 miles, depending on the study. More recent measurements, cross-checked against the 2017 occultation data and improved thermal observations, have narrowed that range considerably, though a small amount of uncertainty remains for both moons even today. That kind of ongoing refinement is normal for objects this faint and this far away. Every improvement in instrument sensitivity tends to sharpen a number that once looked settled, and Haumea's entire moon system has been revised more than once since 2005, without ever contradicting the basic picture of two icy fragments caught in orbit around their much larger parent. Picture the three bodies together. From a distance, one stretched, spinning world at the center, and two smaller fragments still caught in its gravity, decades after whatever event separated them in the first place, still tracing orbits that trace the shape of the very collision that created them. They haven't drifted away. They haven't fallen back in. They're suspended in exactly the kind of arrangement debris settles into after a fight neither side entirely won. If you compared a photograph of the night sky from your own childhood to one taken tonight, you'd struggle to spot a single moving orbit by eye. Most orbits, on human timescales, look frozen. Watch a planet or a moon for a decade, and its path around its parent body looks essentially identical at the end of the decade to how it looked at the start. The kind of motion so slow it might as well be geology. Namaka doesn't cooperate with that expectation. Astronomers tracking Namaka's orbit across roughly a decade of observations, using repeated imaging from the Hubble Space Telescope and large ground-based telescopes in Hawaii and Chile, found something that shouldn't be visible on a human timescale at all. The orbit itself is precessing, tilting, shifting its orientation in measurable, trackable amounts within a period of years, not millennia. Part of the cause is Haumea's own shape. A body this stretched doesn't pull on its moons the same way a sphere would, and that lopsided gravity tugs Namaka's path out of true faster than a rounder world ever could. Part of the cause is Haumea itself, tugging on its smaller sibling every time their orbits bring them close. Measuring the effect at all required an unusual amount of patience, even by the standards of outer solar system astronomy. Namaka is faint enough that a single image says almost nothing useful. The precession only becomes visible by comparing carefully calibrated positions gathered years apart, subtracting out every other source of measurement error, and watching what's left. Early attempts to model Namaka's orbit as a simple, fixed ellipse kept failing to fit the data cleanly. A strong sign in itself that something about the assumption was wrong before anyone had confirmed exactly what. The rate of that precession, once astronomers pinned it down, turned out to be measured in a handful of degrees per year. A slow drift by any everyday standard, but a strikingly fast one for celestial mechanics, where changes are usually described in fractions of a degree per century rather than per year. Haumea completes a noticeable reorientation of its entire orbital plane within a span of time shorter than a single human generation, a pace that would have been considered implausible for any moon anywhere in the solar system. Before Haumea's system forced a reconsideration, researchers have started using the precession rate itself as an additional tool for pinning down details of Haumea's interior that can't be measured any other way, since the exact speed and pattern of the wobble depends sensitively on exactly how Haumea's mass is distributed inside its stretched, three-axis body. That's not a subtle detail. It means the Haumea system isn't a finished arrangement quietly coasting through the dark. It's still actively rearranging itself, visibly, on a timescale short enough that the same telescope, pointed at the same target a few years apart, catches the difference. Whatever violence built this system did not simply happen and then stop. It's still working itself out, which raises the harder question underneath everything measured so far. A rotation this extreme, a shape this stretched, two moons still bound close by. A single strike, violent enough, could plausibly explain all of that on its own. But no single strike, however violent, explains what astronomers found scattered across an enormous stretch of space beyond Haumea entirely, drifting on orbits that all trace back, unmistakably, to the same event. In 2007, astronomers Darren Ragozin and Mike Brown published something that had never been confirmed anywhere in the outer solar system before. A family. Not a family in the loose sense of objects that happen to be nearby. A collisional family in the strict technical sense. A group of separate bodies that share not just similar orbits, but a matching chemical signature specific enough to rule out coincidence. The kind of signature that only makes sense if every member used to be part of the same larger object. If you've ever heard of the Vesta or Nysa families in the asteroid belt, you already know the general concept. Families like this are common enough closer to the Sun, where collisions happen more often and debris has less room to wander before drifting apart. Out in the Kuiper Belt, 4 billion miles from the Sun, in a region so vast and so slow-moving that most collisions are gentle nudges rather than shattering blows, nobody had ever confirmed one. The region is too big, the objects too faint, the timescales too long for scattered debris to still look related after billions of years of drifting. Haumea's family looked related anyway. A dozen or so smaller Kuiper Belt objects, and eventually several dozen candidates beyond that first group. Current catalogues list somewhere in the neighbourhood of 30 confirmed or strongly suspected members, with the exact count shifting slightly as new surveys refine both the orbital and spectral criteria used to test membership. Share Haumea's most unusual trait: surfaces dominated by crystalline water ice, brighter and chemically distinct from the darker, more processed material that covers almost every other object out that far. Most Kuiper Belt bodies are reddish, muted, weathered by billions of years of cosmic radiation. This scattered handful are not. They're pale, icy, and out of place, precisely what you'd expect from fragments of Haumea's own shattered outer shell, flung outward and left drifting on orbits that still, faintly, echo where they came from. Picture that shell the way it might have existed before any of this happened. A layer of clean, bright ice wrapped around a denser interior, the kind of surface every icy world this far out probably starts with. Now picture a piece of that shell knocked loose hard enough to leave the system entirely, drifting for 4 billion years on its own orbit, still carrying the same ice, the same brightness, the same chemical signature as the world it came from. A scattered inheritance nobody was looking for until the pieces started, one by one, refusing to blend in with their surroundings. Confirming membership in the family isn't as simple as noticing an object looks icy. Astronomers cross-check two separate lines of evidence before accepting a candidate. The orbital fingerprint, a specific combination of orbital elements that would only line up this way if the object shared a common origin with Haumea, and the spectral fingerprint, the same crystalline water-ice signature that sets the family apart from the darker Kuiper belt population around it. Objects that pass one test but not the other stay listed as tentative rather than confirmed, and a handful of early candidates have been quietly dropped from the family over the years as better data ruled them out. None of that scattered evidence, on its own, proves exactly how the strike happened, or when, or at what angle. Tracking down that many faint, scattered objects and confirming which ones actually belong to the family has remained an ongoing project, rather than a one-time announcement. Each candidate requires years of follow-up observation to nail down an orbit precise enough for meaningful comparison and spectroscopy sensitive enough to confirm the shared ice signature, rather than a coincidental resemblance. Slow, patient work spread across multiple observatories and more than a decade of survey time. The clearest physical confirmation of the mechanics. Proof that something really did carve material away from Haumea's surface, rather than simply nudging debris loose from orbit, came from somewhere much closer to home. It came from something circling Haumea itself, something nobody expected to find at all. On the night of January 21st, 2017, 10 telescopes scattered across 10 different sites in Europe pointed at the same patch of sky, waiting for Haumea to pass directly in front of a distant star. That kind of event, an occultation, is one of the only ways to measure a faint, distant object's true outline precisely. Watch the star's light disappear the instant Haumea's edge crosses in front of it. Watch it reappear the instant the edge clears, and the timing across multiple locations draws the object's silhouette against the dark with a precision no direct image could match. The technique had already been used to refine measurements of Pluto and several other distant bodies. Nobody organizing that night's observation expected it to reveal anything beyond a slightly sharper outline of Haumea itself. Picture the setup the way you'd picture any of the 10 observers that night. Eyes on a clock, hands on a shutter, waiting for a star to vanish on schedule. The shape came through exactly as expected. Stretched, 3-axis, consistent with everything astronomers already suspected. Then the data kept showing something else, several seconds before the main occultation, and again several seconds after. The star's light dipped slightly and briefly, a shadow crossing well outside Haumea's own outline, in a place where nothing should have been. It was a ring, a narrow band of material, roughly 45 miles wide, circling Haumea at a distance of around 1,000 miles above its surface, tilted to align closely with both Haumea's equator and the orbital plane of Hi'iaka, its larger moon. No object this small, this far from the sun, had ever been confirmed to have one. Rings, as far as anyone understood them before that night, belonged to giant planets with enormous gravity wells, or to a small handful of larger centaurs closer to Saturn's orbit, never to something barely 1/10 the width of Earth, drifting alone at the edge of everything. Here's what most people still misunderstand about rings in general. They aren't leftover debris just sitting quietly in place. They're actively maintained, held to a narrow, stable band by gravity doing precise, ongoing work. In Haumea's case, likely a resonance with the body's own rotation, the ring material orbiting at almost exactly the pace where Haumea's spin and the ring's orbit reinforce each other instead of spreading the material thin. Remove that balance, and a ring this narrow should disperse within a few thousand years, a blink of an eye against the age of the solar system. Confirming a ring this faint took more than one night of data. Astronomers returned to Haumea during subsequent occultations in the years after 2017, watching for the same brief dip in starlight at the same predicted distance before treating the discovery as fully secure rather than a single lucky read of noisy data. Each additional confirmation also sharpened the ring's measured width and distance, refining the picture from a rough detection into a precisely characterized structure, narrow enough that early estimates of its width shifted by several miles between the first announcement and the follow-up studies that came after it, which means the ring isn't simply proof that something violent happened to Haumea once. It's proof that whatever emerged from that violence arranged itself afterward into something precise enough to still be holding together perfectly, undisturbed, 4 billion years later. Try to weigh Haumea yourself, and you'd run into a problem immediately. There's no scale in existence built for a task like that. Astronomers can't put it on one directly either. The orbits of its 2 moons do the work for them instead. The underlying method is centuries old. Johannes Kepler worked out, using nothing but careful records of planetary motion, that the size and period of an orbit are tied directly to the mass of whatever the orbiting body is circling. Point that same relationship at Hiaka and Namaka, measure how fast each one circles Haumea and how far out each orbit sits, and the combined mass of the entire system falls out the other end with real precision, no direct contact required. Roughly a third the mass of Pluto, packed into a body barely a third of Pluto's width. Divide that mass by Haumea's volume, and the resulting density is where the real surprise sits. Most Kuiper Belt objects, built mainly from water ice with only a modest amount of rock mixed in, come out fairly light for their size. Roughly the density of packed snow, or a little denser. Haumea comes out closer to 1 9/10 times the density of water. That's dramatically higher than almost anything else out there its size. It implies an interior that's mostly rock, not ice. A dense core making up the bulk of the body, wrapped in a shell of ice, thin enough to almost be an afterthought by comparison. That composition only makes sense if Haumea differentiated early. If it heated up enough, sometime in its first few 100 million years, for heavier rock to sink toward the center, while lighter ice rose toward the surface, the same layering process that shaped Earth, just built from different materials and finished on a much smaller world. The heat for that kind of sorting, this far from the sun, most likely came from the decay of short-lived radioactive elements mixed into the material Haumea originally formed from, the same mechanism thought to have warmed the interiors of several other differentiated bodies in the outer solar system during their earliest few million years. A body like that starts out with a genuine icy shell worth losing. Density measurements like this one carry their own margin of error, worth acknowledging rather than glossing over. Both Haumea's mass and its volume depend on other measurements. The moon's orbits for mass, the occultation-derived shape for volume, each with its own small uncertainty that compounds when combined. Even accounting for that margin generously, the resulting density estimate stays well above what a body built mostly of ice could plausibly produce, which is why the rock-dominated interior remains. The interpretation researchers keep returning to, rather than a measurement error waiting to be explained away. So now the pieces start locking together, instead of just sitting side by side. A differentiated world, rock at the core and ice at the surface, takes a violent strike. The strike doesn't just spin the body up and stretch its shape. It preferentially strips away the outer material, the ice, the lighter shell, the part sitting farthest from the impact's center of force, while the denser rock beneath stays largely intact. That single mechanism accounts for the spin, the shape, the unusually high density of what's left behind, and the ice-rich, low-density fragments now scattered across the Kuiper Belt as the family. 4 separate anomalies. One event doing all the damage at once. Water ice comes in more than one internal structure, and the difference matters more than it sounds like it should. Fresh ice, newly formed or recently disturbed, arranges its molecules in a neat, repeating lattice. Crystalline ice, the same basic structure as the ice in a glass of water on a kitchen counter. Leave that ice sitting exposed for long enough, out where cosmic rays and ultraviolet light strike it unfiltered by any atmosphere, and the orderly structure slowly breaks down. The molecules stay in place, but the neat lattice collapses into a disordered jumble. Amorphous ice, structurally closer to glass than to a proper crystal. Out in the Kuiper Belt, that breakdown doesn't take long by astronomical standards. Models of radiation exposure at Haumea's distance from the Sun suggest crystalline ice should degrade into the amorphous form within, somewhere on the order of 10 to 100 million years. The solar system is roughly 4.5 billion years old. Every scrap of untouched, exposed ice out there should have gone glassy and disordered a very long time ago. Most Kuiper Belt objects, in fact, show exactly that. Spectra consistent with heavily processed, amorphous or near-amorphous ice. Exactly what the radiation models predict for something that's simply been sitting exposed for billions of years. Haumea's surface hasn't followed that pattern. Spectroscopic measurements of both Haumea and its scattered family members show ice that is overwhelmingly crystalline, fresh-looking, ordered, structurally young, on a body that by every other measure appears to be carrying scars from an event billions of years in its past. Ground-based spectroscopy first flagged the anomaly not long after the family's discovery, and every subsequent measurement, including more recent infrared observations, has continued to confirm it rather than explain it away. The same puzzle shows up in a milder form on several of Haumea's family members too, which matters for ruling out easy explanations. If only Haumea itself showed unexpectedly fresh ice, a plausible answer might involve something specific to the parent body. Leftover internal heat from the original impact, for instance, still slowly working its way to the surface. Fresh-looking crystalline ice turning up across multiple, independently orbiting fragments, scattered over a wide region of the Kuiper Belt, is much harder to explain with a single body's leftover heat. Whatever is keeping the ice young appears to be either a shared property of the whole family or a clue that the entire event happened more recently than the impact simulations currently suggest. Laboratory experiments back on Earth have helped calibrate exactly how fast that degradation should proceed, firing radiation at samples of crystalline ice under conditions meant to mimic the Kuiper Belt's environment, and timing how long the ordered structure survives before collapsing. Those experiments are what give the 10 to 100 million year estimate its credibility. The number isn't a guess, it's a measured rate, extrapolated from physics that can be tested directly under laboratory conditions, rather than only inferred from a distance. Here's where it stops making simple sense. Either something is actively refreshing Haumea's surface, resurfacing it faster than radiation can degrade it, internal heat, a slow cryovolcanic process, something continuing to expose new ice from beneath the old, or the numbers wrapped around the collision itself, the timing everyone has been working from, need to be reconsidered. Both explanations carry real problems. A body this small and this cold, this far from any obvious source of internal heat, isn't an easy candidate for ongoing resurfacing. And a more recent collision creates a different kind of trouble entirely. One that shows up clearly once you start asking how the scattered family has managed to hold together at all. Almost everything measured about Haumea points to a body covered in bright, clean, highly reflective ice. Among the whitest surfaces known anywhere in the outer solar system, closer in brightness to fresh snow than to the dull, weathered material covering most of its neighbors. Almost everything, careful tracking of Haumea's light curve, the same brightening and dimming rhythm that first revealed its shape, turned up something that doesn't fit the rest of the picture. One region, rotating into and out of view every 3 hours and 55 minutes, noticeably darker and redder than everywhere else on the body. If you tracked Haumea's brightness yourself, night after night, you'd eventually notice the same dip everyone else has, a region astronomers now refer to, informally, as the dark red spot. It isn't an isolated case among icy worlds. Both Pluto and its large moon Charon carry their own named dark regions. Pluto's Cthulhu Macula, a vast dusky band along its equator, and Charon's Mordor Macula, a reddish cap at its pole thought to come from escaped gases chemically altered by sunlight before settling back onto the surface. Haumea's spot doesn't obviously match either mechanism. It's smaller, more concentrated, and sits on a body without the kind of atmosphere Pluto uses to redistribute material that way. Spectroscopic attempts to characterize exactly what Haumea's spot is made of have produced more disagreement than consensus. Some studies point to the possibility of ammoniated minerals or salts, materials rarely seen so clearly elsewhere in the outer solar system. Others suggest simple exposed, non-icy rock, or organic compounds concentrated in that one location for reasons nobody has confirmed. None of the proposed explanations has settled the question yet. Pinning the spot's location down at all required stitching together years of brightness measurements taken from multiple observatories, cross-referencing the timing of each dip and rise against Haumea's known rotation period, until a consistent picture of one fixed region, rather than a wandering or intermittent one, finally emerged. That consistency is itself informative. Whatever the spot is made of, it isn't a temporary or shifting feature. It has stayed anchored to the same patch of Haumea's surface for as long as anyone has been tracking it, behaving like a permanent geological feature rather than a passing weather pattern. What's harder to dispute is what the spot implies about Haumea generally. This is not a uniform body. Somewhere on its surface, whether from an impact, an internal process pushing older material upward, or something else entirely, a patch of genuinely different chemistry sits exposed, rotating past our line of sight every few hours, distinguishable enough to spot in data gathered from 4 billion miles away. Some researchers have floated the possibility that the spot marks the exact point of the original impact, the one location on the surface where the collision's chemical signature never fully diluted into the surrounding ice. It's a tidy idea, and an unproven one. Nothing currently rules out a completely unrelated cause, arriving billions of years after the fact from some smaller, later strike with no connection to the main event at all. A body already flagged for one unexplained anomaly after another gains one more. Not resolved, not close to resolved, just another patch of Haumea that doesn't behave the way the rest of it does, filed alongside the ice that shouldn't still be crystalline and the shape that shouldn't still be held. If you tried to reconstruct an event that happened billions of years ago with no surviving direct record of it, you might assume it's little more than guesswork. It isn't, not entirely. Researchers modelling Haumea's formation, among them Zoe Leinhardt and colleagues, publishing detailed impact simulations in the years following the family's discovery, worked backward from what's actually measurable today. Haumea's current mass, its density, its spin, the combined mass of its moons and known family members, and the total amount of energy a collision would need to produce all of it at once. The scenario that best matches the evidence involves a proto-Haumea already differentiated, rock settled at its core, ice layered at its surface, struck by another sizable icy body early in the solar system's history, plausibly within its first several hundred million to roughly 1 billion years, while the outer disk of debris was still dense enough for collisions this significant to happen at all. The strike wasn't a direct, head-on hit. Simulations favour a glancing blow, one that transfers enormous spin into the target, rather than simply shattering it outright. The same physical principle behind why a glancing punch spins a body while a direct one just knocks it backward. That glancing geometry matters. A head-on collision at the energies involved would likely have destroyed Haumea outright, leaving nothing coherent behind at all. A precisely angled glancing strike does something more surgical. It strips a meaningful fraction of the icy shell away in one violent pass, spins the remaining body up to near its structural limit, and scatters the removed material outward, some of it coalescing into the 2 moons still orbiting close by, some of it escaping entirely to become the family drifting across the wider Kuiper belt today. Running these simulations at all requires substantial computing power, modeling millions of individual particles of ice and rock through the moments of impact and the hours afterward, and different research groups working from slightly different starting assumptions about the impactor's size and speed have arrived at scenarios that agree on the broad outline while still disagreeing on the finer details. Testing a simulated scenario against reality means checking it against every independent measurement available, not just the one it was built to explain. A successful impact model has to reproduce Haumea's current spin rate, its axis ratios, its density, the combined mass of the moons and family members, and the rough distribution of fragment sizes seen in the family today, all from one internally consistent starting scenario. Simulations that nail the shape but produce moons too large, or a family too small, or a rotation rate slightly off, get revised or discarded the same way any model gets refined against data it wasn't originally tuned to match. None of that reconstruction pins down an exact date. The simulations describe a mechanism, tested against the physical evidence left behind, not a calendar, and the mechanism, however well it fits the shape, the spin, and the density, still runs directly into the timing problem the ice itself keeps raising. A family this old should not still look like a family at all. If you tossed a handful of gravel into a slow river and came back 1 billion years later expecting to find it in the same clump, you'd be disappointed. Debris fields don't survive forever. Every fragment flung outward by a collision keeps orbiting the sun independently afterward, and every one of those independent orbits stays subject to the same slow gravitational nudging from every large body nearby. Neptune, most of all, close enough to the Kuiper belt to reshape orbits there over long stretches of time. Run those nudges forward for a few 100 million years, and a tight, freshly formed family of fragments should gradually spread out, drift apart, and eventually become dynamically indistinguishable from the general Kuiper belt population around it. Researchers running that math on Haumea's family kept arriving at an uncomfortable number. Models suggest a family this size and this dispersed pattern should become unrecognizable, blended into the background within something on the order of 1 billion years, possibly less. If the collision that built Haumea's family happened as long ago as the impact simulations suggest, potentially several billion years, the family shouldn't still be identifiable as a family today. And yet it is. Astronomers can still pick its members out from the surrounding field, still trace their shared chemistry, still group them by matching orbital characteristics decades after the first handful was spotted. Some researchers have proposed that Haumea's family may simply be an unusually lucky case, a group whose particular orbital geometry happens to resist the normal dispersal process longer than average, rather than genuine evidence that the collision was more recent than assumed. Others find that explanation unsatisfying on its own, arguing that unusually lucky is doing too much work to paper over a discrepancy this large, spanning multiple independent members rather than one or two outliers. The stakes of that disagreement reach beyond Haumea's own biography. If a collisional family this large and this well-defined really can survive for several billion years despite the dispersal models, then those models, used across planetary science to estimate the ages of debris fields well beyond this one system, may need broader revision if instead the family turns out to be much younger than early impact simulations assumed. That reshapes the timeline for everything downstream. How recently the Kuiper belt was still capable of producing collisions this significant, and what that says about how violent the outer solar system remained long after the planets themselves had finished forming. So now there are two timing estimates that don't comfortably agree. The ice on Haumea's own surface argues the resurfacing, or the collision itself, might be more recent than assumed. The dynamics of the scattered family argue the same thing from a completely different direction, that the debris hasn't had the billions of years it would need to fully disperse. Two independent lines of evidence, pointing at roughly the same uncomfortable conclusion, arrived at by researchers who weren't looking for each other's results. Nobody has settled on a final number. Estimates for the collision's age still range from under 1 billion years to several billion, depending on which piece of evidence a given study weights most heavily. What's actually agreed on is smaller. And stranger, whatever hit Haumea, however long ago it happened, left behind a system that is still, by every measure available, unusually young for its supposed age. You might expect, by this point in the episode, that one clean collision explains everything left to explain. Not every attempt to explain Haumea settles for one single collision doing all the work. A newer line of research, developed as the timing problems around the family and the ice became harder to ignore, proposes something messier. Two separate events, spaced apart in time, each responsible for a different piece of what's observed today. In one version of this idea, an early, more distant collision is what originally spun Haumea up and carved away the bulk of the family-forming debris, the event responsible for the shape, the density, and the scattered fragments now drifting across the wider Kuiper belt. A second, later, smaller interaction, perhaps not even a direct impact, but a close gravitational encounter, or the slow collapse of a disk of leftover debris still orbiting close to Haumea after the first event, is what actually assembled the two moons, Hiaka and Namaka, out of material that hadn't yet escaped the system entirely. Splitting the story into two events solves part of the timing tension neatly. A moon-forming event happening well after the main collision would naturally look younger, both in the moon's orbital behavior and in whatever surface ice they inherited, without requiring the entire, much larger family to be implausibly young as well. It also offers a tidier explanation for why the moon's shared chemistry looks almost, but not quite, identical to the families. Close enough to confirm a common origin, different enough in small spectral details that some researchers have flagged as a possible sign the moon's finished forming under slightly different conditions than the rest of the debris. Testing between the one-event and two-event pictures will likely come down to future observations rather than theory alone. Closer scrutiny of exactly how similar the moon's ice really is to the wider families, or a sharper measurement of Namaka's current orbital evolution that could reveal, through careful modelling, roughly how long ago its orbit was first set in motion. Neither test is trivial with current instruments, and neither has produced a definitive answer yet. It doesn't resolve everything. Two events require two separate explanations for why each one happened when and how it did, and the Kuiper belt 4 billion years ago is not an environment anyone can currently model with enough precision to say for certain how likely a second, well-timed encounter would have been. Critics of the two-impact model point out that adding a second event, without independent evidence that it actually happened, risks explaining an inconvenient data point by simply inventing a new one to absorb it. Proponents counter that the solar system's early history was genuinely crowded and genuinely violent, and that assuming only one significant event ever touched Haumea, when the region was full of similarly sized bodies over a period of hundreds of millions of years, may be the less realistic assumption of the two. Both the one collision and two collision versions of Haumea's history remain active positions in the research. Neither one fully closed out, both still being tested against whatever new measurement comes next. If you've followed any of Webb's other headline discoveries, you already know the pattern. For most of the 2 decades since its discovery, Haumea was studied almost entirely through reflected sunlight gathered by ground-based telescopes, useful for tracking brightness, shape, and rough composition, but limited in how finely it could break that light apart. That changed once the James Webb Space Telescope came online and turned its infrared instruments toward the outer solar system. Haumea included, capable of splitting the object's faint light into far more detail than anything available before, unfiltered by the haze and turbulence that blur ground-based observations of anything this dim. The results mostly confirmed what ground-based work had already suggested: a surface dominated by crystalline water ice, unusually bright, structurally too young for its presumed age. But the added precision reopened the question of what else might be mixed into that ice, in smaller quantities, at concentrations too subtle for earlier instruments to catch. Several research groups have reported tentative signs of additional compounds, ammonia-bearing material among the more discussed candidates. potentially linked to the same dark red spot already flagged in earlier surveys. Even setting the specific Haumea question aside, the Webb observations pushed measurements of Haumea's surface temperature and thermal behavior to a level of precision ground-based telescopes had never reached, refining estimates of how efficiently the surface radiates absorbed sunlight back into space. Those thermal numbers feed directly back into the density calculation from earlier in this episode, tightening the confidence around just how rock-heavy Haumea's interior really is. None of those detections has settled into firm consensus. Ammonia is a notoriously difficult signal to confirm this far from the Sun, prone to being mimicked or masked by other compounds in a spectrum this faint, and different research teams working from the same public data have reached different conclusions about how confident to be in what they're seeing. One complicating factor is Haumea's own rapid rotation. Because the dark red region only faces Earth for a fraction of every 3-hour, 55-minute cycle, any single observation risks catching an average of several different surface types blended together rather than a clean read of one specific patch. Confirmation, if it comes, will likely need another dedicated look, ideally timed to catch the dark red region rotating fully into view on its own. Securing the telescope time at all wasn't guaranteed. Webb's schedule is heavily oversubscribed, with proposals from every field of astronomy competing for a limited number of observing hours, and outer solar system targets like Haumea have to make their case for priority against far larger, more heavily funded areas of research. The observations that did happen came through peer-reviewed proposals, justified specifically by the unresolved questions this episode has spent the last several segments describing. What the telescope did resolve, more convincingly than any single point of ambiguous chemistry, is the overall picture. This is not a simple, inert ball of ancient ice. It's a surface with genuine structure, genuine chemical variation from one region to the next, and behavior that keeps generating new, specific, unresolved questions every time a better instrument gets pointed at it. Better data, so far, hasn't simplified Haumea. It's only added more edges to the puzzle. If you tried to predict where a stranger will be standing in 50 years from watching them cross a room once, you'd have roughly the scale of the problem here. Most of what's known about Namaka's shifting orbit comes from a relatively short observational window. A decade or two of tracking against a system that has existed for billions of years. A snapshot, not a full picture. But the trend visible inside that snapshot is clear enough to worry the people running the calculations forward. Namaka's path is more elliptical and more misaligned than Hi'iaka's. And both of those qualities are being actively reshaped by the same gravitational tug-of-war between Haumea's stretched, lopsided gravity and Hi'iaka's steady pull. Run the trend forward, and the long-term outcomes on the table aren't gentle. One possibility has Namaka's orbit gradually settling into a more stable configuration over the coming centuries, the small moon finally finding an arrangement it can hold indefinitely. Another has the opposite ending: continued destabilization, an orbit that keeps drifting until Namaka is ejected from the system entirely, flung into its own independent path around the Sun, severed from the world that once may have been part of it. A third, less likely but not ruled out, involves an eventual close approach to Hi'iaka itself. With consequences, neither moon's current orbit was built to survive. The three outcomes aren't equally weighted in most current models, though none is confidently ruled out. Gradual stabilization is treated as the mildly more likely path by researchers who've run the simulations furthest forward, largely because systems this small tend to lose energy to tidal friction over time, which usually favors settling rather than escalating. But mildly more likely is a long way from confirmed, and the same researchers are quick to note how sensitive the outcome is to details of Haumea's interior structure that still aren't measured directly. Whichever outcome eventually plays out, the process leaves a trail modern instruments are already sensitive enough to keep following. Each additional year of tracking sharpens the orbital model a little further, narrowing the range of plausible futures rather than replacing one guess with another. In that sense, Namaka's fate isn't unknowable so much as it is still actively being measured. One careful observation at a time. By a system too far away and too faint to rush, nobody currently claims to know which of those futures is coming or how soon. The models depend on details. Haumea's exact internal mass distribution, Namaka's exact composition and density, small gravitational effects from more distant bodies that aren't yet pinned down precisely enough to run the simulation with real confidence past a few centuries out. Researchers have compared the situation to trying to predict the long-term fate of a spinning coin balanced on its edge from watching only its first few wobbles. The early behavior narrows the possibilities without fully resolving which way it eventually tips. Every additional year of tracking data adds another wobble to the record and another small constraint on which of Namaka's possible futures remains plausible. What's certain is smaller and, in its own way, stranger. Whatever arrangement exists right now, the one visible in every image astronomers have taken of the system so far, is temporary, not on a geological timescale, not on a scale that requires imagining deep time to feel uneasy about, on a timescale close enough to human history that whoever is still watching Haumea a few hundred years from now may be looking at a genuinely different system than the one visible tonight. Zoom out from Namaka's individual troubles, the way you might step back from a single loose thread to look at the whole sweater. And a similar uncertainty applies to Haumea's entire arrangement. The ring depends on a precise resonance with Haumea's rotation to stay narrow and intact. Slow that rotation down, even slightly, over a long enough stretch of time, and the balance holding the ring together starts to drift out of tune. The elongated shape itself depends on the spin rate staying close to its current value. The same tidal interactions quietly reshaping Namaka's orbit are, over very long timescales, also exchanging angular momentum between Haumea and its moons, a slow enough process to be invisible within any human observational record, but not a process with a reason to stop. None of this is expected to unravel quickly. Tidal effects at these distances, around a body this small, work on timescales that dwarf the couple of decades astronomers have actually been watching. Rough estimates of the exchange rate suggest any meaningful change to Haumea's spin from tidal interaction alone would take longer than the age of the solar system to accumulate, which is itself part of why the current arrangement has survived long enough to be observed at all. But slow is not the same as permanent, and every piece of Haumea's current identity, the exact shape, the precise ring, the specific spin rate that makes the Jacobi mathematics line up so neatly, is a snapshot of a system still very gradually trading momentum back and forth between its parts, the same way it has been since whatever hit it first set all of this moving. Run the same logic backward, and the collision itself starts to look less like a single instant and more like the opening moment of a process still unfolding. The strike delivered the spin and stripped the shell in a matter of hours. Everything since then, the moons settling into their orbits, the ring finding its resonance, the family slowly spreading across the Kuiper belt. Namaka's path continuing to drift has been the same event, still working itself out, just stretched across a timescale too long for any single observer to watch start to finish. Put a number on the pace, and the unease sharpens further. Even the slowest, most conservative estimates of the tidal exchange between Haumea and its moons put meaningful change on a timescale of hundreds of millions to billions of years. Glacially slow by any human measure, but only a small fraction of the age of the solar system itself. Haumea has already had time, in principle, to pass through more than one version of its current arrangement since the original collision, each one gradually trading places with the next. There's a specific unease in that fact. Once it settles in, everything measured about Haumea across this entire episode, the axis lengths, the rotation period, the ring's narrow width, Namaka's tilted path, describes the system as it happens to look during the brief sliver of cosmic time when telescopes on Earth are capable of looking at it. Earlier, the shape would have been different, closer to whatever the collision produced in its rawest form. Later, it will be different again, however slowly that difference accumulates. What gets called Haumea in every paper written about it so far is one frame taken from a very long, very slow film, most of which nobody now alive will ever see. Every measurement in every paper published about this object, going back to 2005, describes the same brief frame with increasing precision rather than a changing one, which is itself a kind of reassurance. The system isn't unraveling on any timescale anyone alive needs to worry about. It's simply, provably, not finished. In the same quiet way a mountain range is not finished just because nobody's watching it lift. If you're picturing every corner of the Kuiper belt as equally well mapped by now, it isn't. Haumea only got discovered at all because of an accident of its own making. That unusually bright, highly reflective icy surface. A body this far away, this small, covered in the same dark, weathered material as most of its neighbours, would sit right at the edge of what even a dedicated survey telescope could detect, faint enough to blend into the noise, easy to miss entirely across multiple observing runs. Haumea's brightness is what pulled it out of that noise in the first place, catching Brown's team's attention, and later, Ortiz's, specifically because it reflected enough sunlight to stand out from a background full of far duller objects. Brightness, in other words, has been doing a disproportionate amount of the work in deciding which parts of the outer solar system humanity has actually met. That raises an uncomfortable implication buried underneath everything else in this episode. If a body needs to be unusually reflective just to get noticed from 4 billion miles away, then an unknown number of similarly violent histories may be sitting out there completely undetected. Bodies that went through the same kind of catastrophic strike Haumea did, spun up the same way, shattered the same way, but happened to end up darker, or smaller, or angled less favourably toward whichever telescope eventually would have looked their way. Estimates of how much of the Kuiper belt remains genuinely uncatalogued vary depending on the size range in question, but for objects smaller than Haumea and darker than its family members, the honest answer from most working astronomers is simply that nobody knows the true population. Only the detected fraction of it. Every new generation of survey telescope, built more sensitive than the last, has turned up objects the previous generation missed entirely, a pattern with no obvious reason to stop just because the current catalogue happens to feel complete. Newer survey projects, built specifically to push deeper into the faint end of the Kuiper belt population than earlier generations of instruments could reach, have already started turning up candidates darker and smaller than anything in Haumea's confirmed family. Objects still being checked against the same orbital and chemical criteria used to confirm membership the first time around. None has yet produced a second confirmed collisional family to rival Haumea's, but the search itself is a tacit admission that the current picture is a floor, not a ceiling, on what's really out there. Each generation of survey has followed the same pattern. Expect a modest handful of new objects, and instead catalogue thousands, forcing yet another upward revision of how crowded the outer solar system actually is. Surveys of the Kuiper belt remain incomplete. By every honest estimate astronomers give, current instruments have mapped only a fraction of what's almost certainly out there, weighted heavily toward the brightest, easiest to spot objects, which means Haumea's family, strange and singular as it currently looks, might not be unique at all. It might simply be the one example bright enough, so far, for anyone to have noticed. The next generation of wide-field survey telescopes now coming online is specifically designed to push past that brightness bias, scanning far fainter and far deeper into the Kuiper belt than any previous instrument, in a deliberate attempt to find out how much of this episode's central mystery is a story about one unusual object and how much of it is a story about an entire hidden population still waiting to be counted. If you've ever wondered why so many distant worlds carry names you half recognize from mythology class, there's a small, deliberate pattern behind it. Classical Kuiper Belt objects, a specific dynamical category Haumea belongs to. Bodies on calm, roughly circular orbits far from Neptune's direct gravitational influence are, by convention, given names drawn from creation deities across different cultures. Figures associated specifically with making things. Birth. Growth. The start of something. The convention grew out of an earlier, looser habit of naming smaller trans-Neptunian objects after underworld or death-associated figures. A pattern that fit the region's cold, distant reputation well enough for smaller, less significant bodies, but started to feel wrong once objects turned up large enough and strange enough to deserve names carrying more weight. Other classical Kuiper Belt objects named under the same convention include Make, after a creator figure from Rapa Nui tradition on Easter Island, and Quawa, drawn from the creation mythology of the Tongva people indigenous to the Los Angeles Basin, a naming pattern that, taken together, reaches across cultures separated by entire oceans to describe a single, shared category of distant, icy worlds. Haumea fits neatly inside that broader pattern while still standing out from it. The one name among that small group whose specific mythology maps this precisely onto the specific physical history of the object wearing it. It's a fittingly gentle rule for a region of space usually described in far colder terms, and it means the naming committee's choice of Haumea, a goddess whose entire mythology revolves around bringing new things into existence through repeated, difficult acts of creation, wasn't really a departure from convention. It followed the rule precisely, just with a namesake that happened to fit its subject's actual history with startling accuracy. A coincidence of category and content that the astronomers involved were, by their own accounts, delighted to land on. There's a smaller pleasure tucked inside that one, too. Haumea is bright enough that under genuinely dark skies, with a capable amateur telescope and considerable patience, it's technically within reach of backyard observation, one of the few trans-Neptunian objects that can claim that. Most of what fills an episode like this sits permanently out of reach of anything but professional-grade equipment. This one, on a clear enough night, does not have to. Amateur observers who have logged the attempt describe it less as a dramatic sighting and more as a quiet confirmation, checking a faint point against a star chart and watching it shift position across successive nights the way nothing fixed in the background ever would. Locating it takes precise coordinates and a star chart rather than luck. Nothing about its appearance in an eyepiece would announce it as more interesting than a dim, unmoving point of light. Knowing what that point of light is doing, 4 billion miles away, is the only thing that makes the moment worth the patience. The difference between a dim smudge in an eyepiece and a whole violent history held entirely in what the observer already knows before looking up. If you had to name a dwarf planet off the top of your head, Pluto would almost certainly be it. So set Haumea next to its better-known neighbour in the same general category, and the comparison flatters Pluto almost everywhere except the one measurement that matters most for this episode. Pluto is larger, rounder, and, by most current models, geologically calmer, without anything resembling Haumea's rotation, its stretched shape, or its scattered family of icy siblings. Pluto spans its day in a leisurely 6.5 Earth days. Haumea finishes the same job in well under 4 hours. Their orbits differ meaningfully too. Pluto sits locked in a stable resonance with Neptune, completing 2 orbits for every 3 of Neptune's, a gravitational relationship that has kept its path predictable and protected for the age of the solar system. Haumea's orbit carries no such protection, sitting in the more loosely governed classical belt, more exposed over time to exactly the kind of slow gravitational disturbance discussed earlier in this episode. Both objects were swept up in the same contentious redefinition of planet that the International Astronomical Union settled by vote in 2006, largely in response to Mike Brown's team finding Eris, a body initially thought to outweigh Pluto outright. Pluto lost a status it had held for 76 years. Haumea never held that status to begin with. It was classified as a dwarf planet from the moment its official designation was assigned in 2008, the same year it received its name, folded into a category that didn't even exist for most of the 20th century. Both bodies now share the category with 3 other officially recognized dwarf planets, along with a much larger number of candidates still waiting on enough data to confirm or rule out the designation. The 2 objects' surfaces tell a similarly divergent story. Pluto's map, assembled from New Horizons' close flyby, shows nitrogen ice glaciers slowly flowing across a basin the size of Texas, a landscape shaped gradually by an active, ongoing cycle of freezing and thawing. Haumea's surface, known only through reflected light rather than a single resolved image, shows something closer to a fossil, ice frozen in a structural state that current models say shouldn't have survived this long, sitting on a body whose entire shape is a direct record of the moment. Violence rearranged it. One world kept slowly changing after its formative event. The other appears to have locked much of its story in place and largely stopped. The comparison matters for a reason beyond trivia. Pluto, for all its own genuine surprises. Mountains of water ice, a hazy nitrogen atmosphere, a heart-shaped glacier photographed up close in 2015, still looks, broadly, like what most people already picture when they hear small, icy world. Haumea doesn't. It's proof that the category holds room for something built by violence rather than by slow accumulation. Spinning at a rate no calm formation could ever produce, dragging visible evidence of its own destruction across a region of space wider than the distance separating Earth from the Sun several times over. If you've been keeping a mental list as this episode went on, put every piece of it back together now, and the picture that emerges isn't a solved case. It's an active one, a body struck hard enough, early enough, to be spun to the edge of its own structural limit, still holding that exact shape today. A ring that shouldn't exist around something this size, still precisely balanced against forces that would otherwise tear it apart within a few thousand years. A family of fragments that shouldn't still be recognizable after this much time. Still, somehow, recognizable. Ice that shouldn't still be crystalline. Still crystalline. A moon whose orbit is visibly shifting inside a human observational record, headed toward an ending nobody can currently predict. Compare that to a body like Jupiter, catalogued by human eyes for thousands of years, or even Pluto, studied in detail since the 1930s. Those objects have had generations of astronomers, working with steadily improving instruments to slowly convert mystery into textbook fact. Haumea has had one generation, working with instruments still catching up to the questions the object itself keeps raising. Every other object covered on a night like this one tends to resolve, eventually, into a settled fact. A number, a shape, a distance, something to rest on before moving to the next thing. Haumea keeps refusing that. Every answer here arrives already carrying its own follow-up question, and every follow-up question turns out to still be open, actively studied, argued over in papers published within the last several years rather than settled decades ago. Part of what makes that unusual is simply how young the entire field of study is. 2 decades separate right now from the object's discovery. Barely enough time, in most areas of astronomy, to move past the initial cataloging stage into anything resembling a settled consensus. Objects studied for a century or more tend to accumulate a kind of institutional certainty, even where real uncertainty remains, simply because the open questions have had generations of researchers to slowly wear them down. Haumea hasn't had that kind of time yet. Almost everything about it is still being actively contested by people who were, in some cases, still in graduate school when the family was first announced. Consider how differently this episode would have read if it had been written even 5 years earlier. The ring wasn't confirmed until 2017. The dynamical tension between the ice's apparent youth and the family's supposed age has sharpened considerably as tracking data has accumulated in the years since. The Webb observations of the surface chemistry are recent enough that some of the papers behind them were still being finalized while this script was being researched. A version of this same episode, written a decade from now, will very likely read differently again. Not because the physics changed, but because the measuring kept catching up to it. That's rarer than it sounds. This far, into a topic, most things this far from the sun have gone quiet, settled into whatever shape gravity and time eventually agreed on together, and stayed there. Something about this one particular world never got the memo, and the researchers still building their careers around finding out why are, by most accounts, in no hurry to see the question close. Sit still. And it's easy to forget that stillness is an illusion. Your body is currently performing rather than a fact about where you are. You're on a planet turning at roughly 1,000 miles an hour at the equator, tracing a wider orbit around the sun at somewhere close to 67,000 miles an hour beyond that, riding a solar system that is itself circling the center of the galaxy at nearly 500,000 miles an hour on top of everything else. None of that motion is something you feel. All of it is something you're doing, constantly, for every second you spend deciding whether tonight's the night you finally fall asleep before this episode ends. Haumea's spin is easy to file away as an extreme, distant curiosity. A fact about a world so far removed from anything human-scaled that it barely seems to belong in the same category as motion you could feel in your own chest. But the physics underneath both is identical. A body in motion holds that motion until something acts on it. Earth's spin, slow and gentle by comparison, is still leftover momentum from the same violent, chaotic period of collisions that built every planet in this solar system, Haumea included, just distributed more calmly across a much larger, much rounder result. Some of the leading models for how the moon itself formed involve a collision not unlike the one proposed for Haumea, a young Earth struck hard enough by a Mars-sized body to fling debris into orbit and leave the planet spinning faster than it does today. Scale that leftover motion up to the level of the entire solar system, and the pattern repeats again. Every planet orbits the sun in roughly the same direction, in roughly the same flattened plane, because the entire system inherited its motion from a single, slowly spinning cloud of gas and dust that collapsed to form it 4.5 billion years ago. Nothing since has been powerful enough to meaningfully redirect that shared, inherited spin. You are moving, right now, along momentum with a traceable origin older than the Earth itself, in a direction chosen before there was any you to have a preference about it. You are, in a very literal sense, still coasting on the leftover motion of a formation process that finished before there was anyone around to notice it happening. Every breath you take tonight moves with the rotating Earth underneath it, has been the entire time, will keep doing so long after you've stopped paying attention and drifted somewhere quieter. The stillness you feel lying here isn't the absence of motion, it's motion so old, so consistent, so evenly distributed across everything around you that your body long ago stopped bothering to notice it as anything unusual at all. Haumea never got that luxury. Its motion stayed violent, stayed asymmetric, stayed extreme enough that nothing about it could ever fade into the kind of background hum. Your own spinning, orbiting, drifting body settled into a long time ago. Go back to the stone dropped at Haumea's equator from the very start of this episode, and there's now enough information gathered to answer the question properly instead of just gesturing at it. Haumea's mass, worked out from its moon's orbits, comes to roughly 4,000 million billion tons. A genuinely large number, and still barely a third of Pluto's. Spread that mass across a body shaped the way Haumea is shaped, elongated and spinning as fast as it spins, and the pull of gravity stops being a single, simple number the way it would be on a sphere. stand at one of Haumea's blunter poles, closer to the body's center of mass and farther from the outward flinging effect of the spin, and the surface gravity there measures meaningfully higher than at the stretched equator, where you're both farther from the center and being flung outward by rotation at the same time, working against gravity's pull. A body weighing a certain amount at Haumea's pole would weigh less standing at its equator, not from any change in mass, but purely from where, on this particular oddly shaped world, its feet happen to be standing. Even the direction you'd need to walk to reach the heaviest point on the surface would depend on where you started, since the gravity gradient runs continuously between pole and equator, rather than jumping between two fixed values, an effect no ordinary planet or round moon inflicts on a visitor. It's a direct physical consequence of everything covered so far tonight, converted into something as simple and personal as a bathroom scale, reading two different numbers depending on which room in the house you stood in to take the measurement. Earth does something like this too. Technically, a person weighs a fraction of a percent less at the equator than at the poles, for the same combined reason of shape and spin, but the effect is small enough on a body this round, and this slow that nobody outside a physics classroom ever notices it. On Haumea, the same effect stops being a rounding error and becomes the headline. Extend the thought one step further, and the direction down itself stops being a fixed idea on a body like this. On Earth, down is simply toward the center, unambiguous no matter where you stand. On Haumea, the combined pull of gravity and the outward shove of rotation add together differently depending on your exact position, meaning the true direction of down would tilt slightly away from straight toward the center almost everywhere except the poles and the equator themselves. A small, strange correction that a visitor's inner ear would eventually have to learn to compensate for, the same way astronauts learn to override the disorientation of freefall. That's the whole shape of this episode, really. Condensed into one imagined scale, every anomaly traced back to the same event. Every measurement, however abstract it sounds on paper, eventually reducible to something as concrete as where, exactly, you would stand. It's a strange kind of intimacy with an object nobody has ever touched, knowing, with real confidence, exactly how its gravity would treat a body standing on it, despite having nothing but reflected sunlight to build that confidence from. You could be forgiven for treating Haumea as a special case, the one confirmed example of a small, icy world visibly wearing the aftermath of a catastrophic strike, and understandably so. But the broader implication buried in that story is less about Haumea specifically and more about how planetary science generally assumed small bodies form in the first place. For decades, the default picture of how objects like this come together involved slow, gentle accumulation. Dust to pebbles, pebbles to boulders, boulders to full-sized bodies, each step gradual, each collision gentle enough to add material rather than remove it. Haumea is direct physical evidence that the gentle version of that story isn't the only version. Somewhere in the crowded early solar system, violent, shape-altering, spin-altering collisions happened too, and at least one produced a result dramatic enough and lucky enough in its surviving debris to still be studied in detail 4 billion years later. Planetary scientists studying other categories of small bodies have started asking whether some of the puzzling shapes and spin rates seen elsewhere, among certain asteroids, among a handful of other distant Kuiper Belt objects with unusually fast rotation of their own, might carry a quieter version of the same violent history, one that never left behind a conveniently bright family to confirm it. Even within the well-studied asteroid belt, a small number of bodies show rotation rates and shapes odd enough that researchers have floated similar violent explanations without ever confirming a scattered family to match. Without that confirming family, the one piece of evidence that turned Haumea from a curiosity into a certainty, those other cases remain permanently stuck at the level of plausible suspicion, unable to graduate into confirmed history the way Haumea's story did. the question that leaves hanging isn't really about Haumea at all. It's about how many other small worlds across the solar system, less fortunate in leaving behind an identifiable family or a conveniently bright surface, carry a similar violent history, with no remaining way to prove it. The two pictures aren't in competition. Exactly. Gentle accretion almost certainly built the overwhelming majority of everything orbiting the Sun, Haumea's own core included, before anything struck it. The violent exception describes what happened afterward, to a body that had already mostly finished forming the ordinary way. Formation and destruction aren't opposites here. They're sequential chapters in the same object's history, and Haumea happens to be one of the rare cases where both chapters left evidence still legible today. There isn't a clean, tidy analogy for holding both versions of solar system formation in mind at once. The slow, patient accretion story and the sudden, shattering exception sitting right alongside it. Try holding them separately instead, without collapsing one into the other. Most of what built this solar system happened slowly, gently, over unimaginable stretches of time. And at least once, not far from here in cosmic terms, something happened fast. And the two versions of the story, patient and sudden, ended up standing side by side in the very same object. If you'd asked any astronomer before 2013 whether a body this small could hold a ring, you'd likely have gotten a confident no. Before Haumea's ring turned up in that 2017 occultation, the object that had already forced astronomers to rethink where rings could exist was Chariklo, a much smaller body called a centaur, orbiting between Saturn and Uranus, confirmed to have a narrow double ring system back in 2013. Chariklo isn't in the same dynamical category as Haumea, and it isn't nearly as large. But the discovery mattered for exactly the same reason. Rings, everyone had assumed, belong to giant planets, bodies massive enough to generate the kind of gravitational environment thought necessary to hold debris in a stable band. Chariklo broke that assumption first. Haumea broke it again, on a body classified as a dwarf planet rather than a leftover fragment, at a distance from the Sun more than 4 times farther out. Since those two discoveries, astronomers have flagged at least one more candidate ring system around another centaur, based on similarly brief dips in starlight during occultation attempts, though the case there remains less firmly confirmed than either Chariklo's or Haumea's. 2 confirmed cases and 1 likely third don't make a pattern yet, not in any statistically rigorous sense, but 2 cases where nobody expected even one is already enough to reshape the working assumption. The resonance that seems to hold Haumea's ring in place adds a further wrinkle worth noting. Unlike the well-known rings of Saturn, shepherded by the gravity of small moons orbiting directly within the ring itself, Haumea's ring may be sustained largely by its own rapid spin, rather than by any dedicated shepherding body. If that turns out to be correct, it would represent a genuinely different mechanism for ring stability than the one textbooks have relied on for decades, built entirely around the giant planets everyone actually had data for. Rings, it now looks like, aren't a rare privilege reserved for the largest bodies in the solar system. They may simply require the right combination of a compact source of debris, a stable resonance to hold that debris in place, and enough time left undisturbed for the arrangement to settle. Conditions that turn out to be less exclusive to giant planets than anyone previously had reason to think. Saturn's rings, for comparison, span roughly 170,000 miles from inner edge to outer edge, built from an almost inconceivable quantity of ice and rock accumulated over the planet's entire gravitational reach. Haumea's ring, at roughly 45 miles wide, would fit inside Saturn's ring system many hundreds of times over. Scale is where the comparison ends and the shared underlying physics begins. The same basic gravitational bookkeeping governing systems separated by a difference in size larger than the difference between a coastline and a single grain of sand on it. That reframing turns Haumea's ring from an isolated oddity into a data point in a much larger, still mostly unanswered question. how many other small, distant bodies out past Neptune are quietly carrying rings of their own. Too faint and too far for any occultation to have caught yet, you met this same slow tilting behavior a few segments ago, without a name attached to it. Namaka's shifting, precessing orbit, and the wider family's difficulty holding together over long stretches of time, both trace back, at least in part, to a gravitational effect known as the Kozai mechanism, a slow, cyclical exchange between an orbit's shape and its tilt, driven by the gravitational influence of a more distant, more massive body nearby. The mechanism was first worked out mathematically in the 1960s, independently by the Japanese astronomer Yoshihide Kozai, and, around the same time, by the Russian astronomer Mikhail Lidov, in each case as an abstract problem in orbital dynamics rather than an attempt to explain any specific object. In the Haumea system specifically, Haumea's own lopsided gravity and the periodic pull of the wider solar environment both contribute pressure in this direction, nudging Namaka's orbit to trade eccentricity for inclination and back again, in a slow, repeating cycle rather than settling into anything fixed. The same basic mechanism operates well beyond Haumea. It reshapes the orbits of distant asteroids, complicates the long-term stability of some exoplanet systems observed around other stars, and factors into why loosely bound families of objects throughout the solar system, not just this one, tend to blur and disperse over sufficiently long timescales rather than holding a tight, permanent formation. Elsewhere in the solar system, the same mechanism helps explain why certain asteroids maintain oddly tilted, oddly stretched orbits despite ordinary origins. And it turns up again, translated into a very different context, in models of how some exoplanets end up on orbits sharply misaligned with their star's equator. A gravitational effect worked out to explain nothing more exotic than distant satellites has quietly become one of the more universal tools in modern orbital dynamics, turning up wherever a small body finds itself caught between the competing pulls of something close and something large and far away. A tug of war with no clear winner, only a slow, permanent trade between one kind of orbit and another. Kozai and Lidov each arrived at the insight from pure orbital mathematics decades before anyone had the observational tools to catch the effect happening in real time anywhere in the solar system. Namaka's rapidly shifting orbit is one of the clearest real-world demonstrations of their mathematics now available to astronomers. A slow-motion cycle, worked out on paper in the 20th century, playing out visibly around a world nobody had even discovered yet when the equations were first written down. Understanding the mechanism doesn't resolve Haumea's specific timing problem. It only explains, more precisely, why the problem exists at all. Why a family this old should have scattered. Why Namaka's orbit doesn't behave like a settled ordinary moon. Why nothing in this system has the fixed, static quality most orbital diagrams imply. The forces at work are well understood. What they're going to do to this particular arrangement on this particular timeline still isn't. Modeling the Kozai cycle precisely enough to predict Namaka's specific future requires knowing quantities. Haumea's exact internal mass distribution chief among them, that remain estimated rather than measured, which is part of why the same underlying mathematics that explains the misalignment so cleanly still can't say with confidence exactly where that misalignment leads. You may have felt it already. Sitting somewhere underneath the last several segments, a specific discomfort in a story where the same single event that destroyed something is also the reason two moons and a scattered family of icy worlds exist at all. Nothing about the collision that struck Haumea was gentle or intentional, or anything resembling the deliberate creation myths humans have told about how worlds usually come to be. It was violent, sudden, catastrophic, indifferent to what it produced. And what it produced, afterward, includes almost everything that makes this particular system worth an entire episode. The moons, the family, the ring's precise resonance, even the shape itself held in an equilibrium. A mathematician worked out on paper a century and a half before anyone had proof it applied to anything real. Nothing about the physics required that outcome. A slightly different angle, a slightly different mass, a slightly different velocity at the moment of impact, and Haumea's story ends in fragments too scattered and too small to ever be traced back to a shared origin. No family, no moons, no name drawn from a goddess of birth, just debris indistinguishable from the general Kuiper Belt population around it. The version of Haumea that exists to be studied tonight is the version where destruction happened to leave behind something coherent enough to survive. Compare it, for a moment, to the leading theory for how Earth's own moon formed. A young Earth struck by a body roughly the size of Mars. Debris flung into orbit, eventually gathering into the single companion still overhead every night. That impact, like Haumea's, was neither gentle nor aimed at producing a moon. It was simply violent enough, at the right angle, to leave something orbiting afterward, instead of nothing at all. Two entirely different collisions on two entirely different kinds of world, both settling into the same basic outcome. Destruction that happened to leave a companion behind, rather than just a wound. It's worth resisting the urge to smooth that observation into something more comforting than it actually is. This isn't a story about resilience, or about beauty emerging from chaos on purpose. Nothing about the collision cared what came out the other side. The moons could just as easily have been debris too small and too scattered to ever coalesce. The family could just as easily have dispersed within the first few 100 million years instead of somehow still being traceable today. What actually happened sits closer to a coin landing on its edge than to any kind of guaranteed outcome. Most collisions violent enough to matter at all end more simply than Haumea's did. Pure destruction. Fragments too small and too fast to ever be traced back to a shared parent. No name, no story, nothing left coherent enough for a future telescope to single out. The Kuiper Belt is almost certainly full of exactly that kind of quiet wreckage. Unremarkable and unremarked upon, precisely because nothing about it survived clearly enough to draw attention. That's not a moral about the universe rewarding anything. It's closer to an observation about what survives long enough to be found at all. Not the gentle formations, most of the time, but the violent ones, lucky enough to leave a shape behind worth naming. History, cosmic or otherwise, keeps a strange kind of record that way. Not everything that happened, only what happened to leave something behind, coherent enough to still be read. You'd be forgiven for assuming, after an episode this detailed, that a probe had flown past Haumea at some point. None did. Everything covered tonight, the shape, the spin, the ring, the moons, the family, the density, the crystalline ice, the dark red spot, nobody can fully explain was learned without a single spacecraft ever making the trip. No orbiter has circled Haumea, no lander has touched its surface, and no close flyby has photographed it directly, the way New Horizons photographed Pluto in 2015, close enough to resolve mountains, plains, and a hazy atmosphere in a single pass. Everything known about Haumea has arrived as light, reflected sunlight, gathered across 4 billion miles, split into spectra, timed during rare occultations, and interpreted by researchers who have never seen this world as anything more than a moving point, too small for even the best available telescopes to resolve into a disk. That's worth sitting with plainly. Without dressing it up, nobody currently has a funded mission plan to change that. A dedicated flyby, similar in scope to New Horizons, would take well over a decade to reach Haumea, even if approved and launched immediately, and no space agency has committed to funding one. Proposals have been sketched out in academic papers, the way proposals for dozens of unfunded missions are sketched out every year, but a sketch on paper and a launch date are very different things, and nothing currently scheduled closes that gap. A handful of proposed concepts have imagined faster, cheaper alternatives to a full dedicated mission. A small telescope with a name like Haumea Explorer a rideshare payload attached to some other outer solar system mission already headed in a useful direction, none of which have progressed past the earliest planning stages. Every real mission that has ever reached the outer solar system, from Voyager to New Horizons, took decades from first proposal to launch, and Haumea currently sits nowhere on that multi-decade pipeline. Everything this episode has described as fact is the best current interpretation of indirect, distant measurements, genuinely rigorous, cross-checked across multiple independent methods, but still, at bottom, inference rather than a photograph. That's not a weakness unique to Haumea. It's the condition almost all of astronomy operates under. For almost everything beyond the handful of worlds a spacecraft has actually visited, Haumea simply makes the condition harder to forget. Because so much of what's strange about it, the ring, the spot, the shifting moon, sits right at the edge of what current methods can detect at all. That gap between inference and direct observation is exactly what keeps researchers publishing new papers about an object discovered 2 decades ago, rather than moving on to something less examined. Every new instrument, every new occultation, every new hour of telescope time granted is another chance to trade one layer of inference for something slightly more direct. Not a photograph yet, but one step closer to it than the measurement before. Some of what's been described tonight will very likely be revised. The exact timing of the collision, the precise cause of the dark red spot, whether one impact or two produced everything currently visible. Science, working this far from direct observation, stays honest by holding its conclusions loosely. And Haumea, more than almost anything else covered on this channel, is still very much a conclusion held loosely. That looseness isn't a flaw in the process. It's the process working exactly as intended, refusing to harden into certainty faster than the evidence actually allows. Step outside at noon, anywhere on Earth, and you'd feel it immediately. The sun overhead delivers roughly a kilowatt of energy to every square yard of ground it touches, enough to warm skin within minutes, enough to power the entire planet's weather. Travel outward to Haumea's distance, somewhere around 43 times farther from the sun than Earth sits, and that same patch of sunlight has spread itself across an area roughly 1,800 times larger than it covered back home. It's simply been stretched thin enough that noon on Haumea would look, to a human eye, less like daylight and more like a very bright, very distant star. Technically the brightest object in that sky, and still nowhere close to what day means anywhere closer in. That thinning follows a strict rule. The same inverse square relationship that governs how any light spreads outward from any source. Double the distance, and the same light covers 4 times the area, diluted to 1/4 of its original intensity. Haumea sits roughly 43 times farther from the sun than you do right now, which means sunlight there carries somewhere in the neighborhood of 1/900th the strength it has at Earth's surface. Close enough to the popular shorthand of 1,000 times fainter that the comparison holds up as more than just a turn of phrase. Surface temperatures out there settle into a narrow, brutal range, hovering somewhere between 30 and 50 degrees above absolute zero, cold enough that nitrogen and most other common gases would freeze solid on contact. Cold enough that the only reason Haumea isn't uniformly featureless is that its ice happens to be stable at exactly this kind of cold. A few 100 million miles closer to the sun, that same ice would have sublimated away entirely, boiling off into space over a comparatively short cosmic time frame. A little farther out, and nothing about the chemistry driving this episode's central mystery, the crystalline structure, the density calculation, the reflectivity making the whole object bright enough to notice in the first place, would look the same. Distance from a star turns out to draw a surprisingly narrow line between world that keeps its story written on its surface for billions of years and world with no durable surface left to read at all. Move any of the icy bodies covered on this channel meaningfully closer to the sun and the record they carry. The ice, the color, the fine structural detail spectroscopy depends on, starts erasing itself within a comparatively short span of time. Move them farther out, and nothing changes fast enough to matter. But nothing about their formation would necessarily produce the same chemistry either. Haumea sits inside a fairly forgiving stretch of that range. Cold enough to preserve, close enough to have formed from familiar enough material for the comparison to other icy worlds to hold up. That's the quiet, easy-to-miss condition underneath everything covered so far tonight. Haumea's entire, strange, violent story only reads the way it does because it happens to sit in exactly the narrow band of distance, and exactly the narrow band of cold where ice this old can still exist as ice at all. If you travelled out past Neptune tonight, expecting to dodge debris the way spacecraft do in movies, you'd be waiting a very long time for anything to nearly hit you. Nothing out there collides with anything very often anymore. The Kuiper Belt today is a genuinely quiet place. Its objects spread across such enormous distances from one another that meaningful collisions have become vanishingly rare events, the kind of thing that might happen to any given object once across the remaining lifetime of the Sun, if that. The environment that produced Haumea's collision doesn't exist out there today. It existed once, in a narrow, violent window early in the solar system's history, and then it closed. That window is tied to a period researchers refer to, collectively, as the era of giant planet migration, a stretch of the solar system's first several 100 million years during which Jupiter, Saturn, Uranus, and Neptune weren't yet settled into their current, stable orbits. Models of that migration, developed and refined over the past 2 decades, suggest Neptune in particular drifted substantially outward from where it originally formed, ploughing through a much denser, closer packed disk of icy debris on its way to its current position. That ploughing motion scattered material violently in every direction. Some of it flung inward toward the inner solar system, some of it ejected from the solar system entirely, and some of it stirred into the crowded, collision-prone environment that could plausibly have produced an event like the one that struck Haumea. Evidence for that migration doesn't rest on Haumea alone. The same models that describe Neptune's outward drift also explain the Kuiper Belt's oddly structured population of resonant orbits. Objects trapped in specific, repeating orbital relationships with Neptune that are difficult to produce any other way. And they line up with a spike in impact craters recorded on the Moon and other inner solar system bodies dated to roughly the same general period. Several independent lines of evidence, developed by researchers working on entirely different questions, keep converging on the same turbulent early chapter. Once the giant planets settled into their current orbits, that violent stirring largely stopped. The Kuiper Belt thinned out, spread out, and slowed down, settling into the calm, sparse arrangement astronomers observe today. The math behind that migration remains an active area of research in its own right. Refined across multiple competing versions of the model, since the idea first gained traction in the early 2000s, each version tuned to match a slightly different slice of the evidence. The exact resonant orbits observed, the exact timing of the inner solar system's crater record, the exact present-day positions of the outer planets. Whatever window allowed a collision like Haumea's to happen has been closed for billions of years, which means Haumea isn't just a record of one specific ancient impact. It's a record of an entire phase of solar system history that no longer exists anywhere for anyone to observe directly. Preserved, by chance, in the shape and spin of one leftover world. Right now, while this plays, Haumea is still turning. Somewhere on its stretched, 3-axis surface, a point at the equator is moving sideways faster than a point on Earth's equator moves in the same instant. The same fact this whole episode opened with, still true, still happening, 4 billion miles away, completely indifferent to whether anyone on a much calmer, much rounder world nearby happens to be listening. The ring is still holding its narrow, precise band above the surface. Haumea is still tracing its steady 49-day orbit. Haumea is still drifting through whatever slow, uncertain reshaping its path is currently undergoing on a timeline nobody has fully worked out. Somewhere on the surface, the dark red patch nobody can quite explain is rotating, once again, into or out of view. None of it is waiting for an answer. None of it has paused to be studied. It was already in motion long before the first telescope ever caught its light, and it will still be in motion long after every question raised tonight eventually gets settled, one way or another, by researchers not yet born. Every measurement gathered across this entire episode, the axis lengths, the density, the ring's narrow width, the family's stubborn persistence, the ice that refuses to age the way it should, describes a system caught mid-motion, not a finished object filed away and closed. New instruments will keep sharpening the numbers. The timing dispute between the ice and the family will likely resolve, one way or another, within the working lifetime of researchers active right now. The dark red patch will eventually get an explanation precise enough to stop being called merely a spot. None of that revision changes the plain facts sitting underneath all of it. Something struck this world hard enough, early enough, that it is still, this many billions of years later, visibly turning because of it, somewhere in a quieter part of the sky, far closer to home. You are also still in motion, carried by the same kind of leftover momentum, on a world calm enough that you've long since stopped noticing. That's the difference between the two stories, in the end. Not that one world moves and the other doesn't. Both are still moving. Right now, exactly as they have been the entire time. One simply settled into a shape gentle enough to disappear into the background. The other never got the chance, and won't get one. Not tonight. Not for a very long time still to come. If ever. If the physics holding it together has its way. A stone, dropped at that equator, right now, would still fall along the same curved path described at the very beginning of this episode, pulled by a shape mathematics predicted, spun by a collision nobody witnessed, still unresolved in exactly the ways that make it worth returning to. We've drifted a long way from where this episode began, through a shape a 19th-century mathematician predicted before anyone had proof it existed anywhere. Through a collision nobody witnessed, and two teams who each believed they'd found its aftermath first, through a ring nothing this small was supposed to hold, and a family of icy fragments still refusing to disperse on schedule. We've stood, in whatever way this kind of standing works, on a world where the pull under your feet changes depending on which direction you're facing, and where a stone falls along a curve no calm, gentle formation could ever have written. Somewhere past Neptune, in the coldest, quietest part of the solar system, that world is still turning. Right now, faster than anything its size has any right to. It doesn't know it was named after a goddess of difficult birth. It doesn't know two teams once argued over who saw it first. Or that a ring above its surface waited 12 years past its discovery to be noticed. Or that its own moons are still drifting toward an ending nobody has worked out yet. It is simply still spinning, the way it has been since something struck it hard enough to matter. 4 billion miles from anyone keeping score. You're closer to that story than the distance suggests. Not because you're spinning that fast, or shaped that strangely, but because you're made of the same leftover momentum, the same inherited motion, the same slow trade between violence and what violence happens to leave behind. Every world in this system, including the calm, round, forgiving one currently holding you up, carries some version of a collision in its history. Most of them settled quietly enough to stop showing it. Haumea didn't get to. If your eyes feel heavy, let them close. That's not the episode failing. That's the episode working exactly the way it was built to. If this felt like the kind of place you want to come back to, Leave a comment when you wake up and tell this quiet universe what part of the night found you. And if you're still here, still listening, still turning something over before the dark takes the rest of it, the next chapter is waiting, whenever you're ready for it. There's no wrong version of how tonight ends. The universe will still be here when you wake up. So will we. Good night.